Hey guys, it's Friday. Wearing my new t-shirt, Athens Tech, Spring Fling. Where does it say that? Spring Fling 2021. Brand new as of yesterday. Playing for you, spinning the tunes here is The Cure. Friday, I'm in love. Don't make me dance now. Don't make me dance. Break out my dance moves. All right, enough of that. We'll tune him down. So, as promised, we're going to take a look at the next section in Unit 4, which is called 7.6. What is that sucker called? Word problems? They come up with a cute name for it. But that's what it really means. Let's see, what's it called? Scroll. Modeling with trigonometric equations. And they got some nice video lessons. Some of these will be useful for showing the problems. Probably do a better job explaining it than I might be able to. Or in the least different, get a different perspective. Multiple perspectives is always good. Anyone that tells you to hear something only their way, personally, in my experience in life, you gotta be suspicious of those people. Those people are trying to sell you something, trying to make you think like a sheep. Okay to question. How you learn. Right? Right. Anywho, let's jump right in it. All right, so it says find a possible formula for the trigonometric function represented by the given table of values. So they just give us a bunch of ordered pairs, and we're supposed to figure out what trig equation is going to model that set of data. That sounds like grown-up math right there. Yeah, this is non-trivial. This is real. This is real math right here. Which kind of makes me all tingly. I'm liking this. So let's just plot these points in Desmos, and then we'll go from there. I have no idea what's going to come up next on YouTube. Oh, more Cure. This is good. Just teaching you some good music. All right. So I've got all the points in there, I believe. 0, -5, he's there. 2, -8's there. 4, -5. 6, -2. What happened to 8, -5? Oh, I got a little. Let's cut that out of there. All right, so that's him. Made a little mistake. That's him. There's the last one. Okay. All right, so that's what we're supposed to get the equation for. So you can tell what the midline, remember the midline? That's the midline. That's at -5. So we could graph that horizontal line, which is not really part of the graph, but is a characteristic of the graph, and the fact that this midline exists. Let's make it a, how did we do that before? Yeah, hold it down. Make that a dotted line. It's too much dots. So maybe we can make it thinner. I don't know, 1. Then let's go with, that looks prettier. All right, so there's our midline. And we're going to figure us out an equation. So let's move this out of the way so we got plenty of room to write. Because I'm gonna create a screenshot that we can write on. Okay, so you first have to figure out, all right, so this is clearly sinusoidal. So if you were to draw a picture, overlay a picture on top of this, it's going to look something like that. This is Robert Smith, by the way. Look him up. It's an English guy. Been doing this a long time. Okay, so you got a choice. Since it's a sinusoidal, you can go with either sine or cosine. I'm going to go with sine because it looks to me like, remember, sine naturally goes through the midline at the origin. So we use sine, then basically we don't have to worry about a shift left or right. Does that make sense? And then you can see that this one's been reflected because normally if you look at a typical sine graph, let's do that. So let's get a, how do I do that? New blank graph. All right. So let's look at y equal sine x. All right, so see, normally sine goes up first and comes back down. So it's been, so this is what we noticed already. So it's been reflected by having a negative in the front, and it's been shifted down to have a new midline at -5. Already we're kind of on our way. So let's get back to ours. All right, so we've got, so far, we're going to use sine, because that seems to fit easier than cosine. We can make cosine work. You just have to shift it left or right. Remember, sine and cosine are basically the same in terms of the graphs, except for that 90-degree shift. They're out of phase from each other by 90 degrees. Right, so we know we're going to have a negative. And that's what made it go down first instead of going up first. We know that the amplitude seems to be, this is -5 is the midline down to -8, so the 3. So remember the amplitude is half the distance from the highest to the lowest. So that's 6 units, which means from the midline to either the valley or a peak is 3 units. So 3 is our amplitude. All right, so normally it's going to be B. B is the, remember your standard form. So it's y equals A, which is the leading coefficient, times x minus I forgot the sign, didn't I? Forgot the trig function. Y equals A times the sine of B x minus C plus the vertical shift D. Oh, by the way, we can stick the vertical shift down at the end. It's going to be -5. That's what shifted the whole thing down 5 units. To have a new midline of being at y equal -5 instead of y equal 0, instead of the x-axis. So really, we're only missing a couple of things. I don't think there is a phase shift because we haven't been shifted. We don't need a phase shift because it's still going through the y-axis at the midline value. So there is no phase shift for this one. So it's just 0. So I don't need to write anything. So really the only mystery is what coefficient goes in front of x. All right, so it's 2 pi, remember, is your standard period for sine. And then we've got the observed period. So I'll just call it OP for observed period. So that seems to be, see, how far is this? What are these values? Oh, I can't even see them. So that's -5, 1, 2, 3, 4. -5, 4. And -5, 8. So it finished its cycle in 8 units. So the observed was just straight up 8 units. So if I wanted to solve for B, I basically need to cross multiply and solve this thing. Now I can get cute with the math, and I can think of that as 8 over 1 and just flip this whole proportion. So that'd be 1/8 is equal to B over 2 pi. Now you cross multiply, and you end up with, and why multiply this by 8 just to go back and divide by 8 just to undo it? So I'm just going to leave the 8 where he is. So I'm going to cross multiply this way and let that stand, let that be it. So 1 times 2 pi over 8 equals B. And then simplify that, the 2 and the 8 simplify and gives me pi fourths. So B is that coefficient that needs to go in front of x. So pi fourths x. That's our equation. So let me look at it one more time, see if I can retain it long enough to write it down. And we'll check it. So y equals, oh, let's go back to, let's not do that one. Where's the other one? Is he still there? Oh, I closed him. How disappointing. I didn't know I closed the whole thing. I Swanee, as my mom used to say. You know, my mom didn't cuss. She didn't swear often. So she was kind of creative. She'd say, Lord love duck. It's a good South Georgia. I don't want to swear, but I really feel like swearing kind of thing to say. She'd say, Lord love duck. Or, what was it? Shoot a monkey. Oh, shoot a monkey. Only in South Georgia, baby. You got to be below that line to get that kind of quality. Quality phrases right there. All right, let me do this again. I want to show that it goes to those points. So I was really dumb to close that. Where's this silly thing? There it is. All right. So let's see here. Let's do it one more again, as my granddad would say. One more time. This music is bothering you? Good. You need to expand your horizons. You don't need to listen to the same old all the time. I have to love this, but appreciate it. Appreciate that it is music. That's maybe different than what you usually listen to. All right, so our equation is supposed to be, and it should go through all those points, we hope. Y, oops, y, ah, y equals negative 3 times the sine of pi fourths x, no phase shift, and then a vertical shift of 5. Look at that, look at there, look at there. Ain't that pretty? It hits everyone exactly where it ought to, where it's supposed to. That's beautiful. Beautiful, beautiful. So that's our answer. Y equals negative 3 times the sine of pi fourths x minus 5. So we got that. The hardest piece was getting that coefficient in front of x. You have to remember that the standard period is 2 pi, and we needed that b value. And so I need to observe from our ordered pairs being plotted what the period seemed to be, and it seemed to be 8 units from the start of the period to the end of the period. I could have started here and ended here. It's still 8 units apart. You could have different stopping and starting places. Just need to complete the cycle, need to complete the period. And that was 8 units. Then I solved for B, and there he is, pi fourths. That was the hardest piece of the puzzle. There we go. All right, so y equals, doing this for the folks that might want to look at the transcript later. Negative 3 times the sine of pi fourths x, close parentheses, minus 5. Okay, number 2. Find a possible formula. I ain't really into this one, but y'all gotta have something fun to do. I'm gonna skip that one. Okay. Outside temperature over the course of a day can be modeled as a sinusoidal function. That means either sine or cosine, right? Suppose the temperature varies between 67 degrees Fahrenheit and 89 degrees Fahrenheit. It didn't really transfer very well, did it? I guess it didn't have the font, didn't have the special symbol, or didn't know how to find it or whatever. So it varies between 67 and 89 during the day, and average daily temperatures first occurs at 12 a.m. How many hours after midnight does the temperature first reach 84 degrees Fahrenheit? Okay, so that's a lot to unpack. So we're going to have a little break. I'm not going to be able to do the whole scale, so that's a little break in the action. So we're going to pick up the scale up the vertical axis at that 67. So we've got lows of 67, highs of 89. And it's basically saying that at midnight, when we start our observations, so right here on the y-axis at time t equals 0, midnight, then we're at an average. We're at the average daily temp. So what's the halfway point between 67 and 89? That's the question. So 89 minus 67 is 22. So there's a 22-degree range from the low to the high. So that means that the average daily temp is right there in the middle to 11 degrees. I need to either go up from 69 or down from 84. It does not matter. But I need to find out what the average daily temp is. So let's add this to 67. So 67. 78. So the average daily temperature is 78 degrees. And they're saying that at midnight we're at that average daily temp. So that's our midline. Our midline is has equation y equals 78. All right, now, is it going to go down from here or up? Well, unless there's some natural disaster catastrophe, you're cooling off after midnight. So this is going to be an inverted, it's going to be reflected. So if I'm using sine, for example, it's going to be like that last problem. It's going to have a negative in front to make it go down first, instead of what it normally does, which is go up and down, up and down. It's going to go down, then up. So I'm going to go down. And then it says, how many hours after midnight does the temperature first reach 84 degrees Fahrenheit? All right, so it's going to have to go down, hit that minimum of 67 degrees at some point. Let's say it's right there. So it hits that minimum at 67. Then it comes back up. It starts to warm up again because the sun's coming up. And then it hits that average daily temp of 78 again. And then it's coming along, coming along. The sun's starting to bake, starting to warm up a little bit. Then eventually it hits that high of 89. They tell us the high is 89. And then it comes back down eventually and hits that 78 again. When? At midnight. So this took 24 hours. That's a 24-hour period. That's a day. So that means, according to this, the way this one behaves, and they're the ones that tell us it's sinusoidal. So we know it's smooth and continuous, and it's periodic. And I can't think of another way this would happen. Do you? I mean, it's not going to like get cold and then warm up to 89 and then come back down all before lunch. The world doesn't work that way. It's going to cool off all during the night and hit its minimum sometime before breakfast and warm back up. Here's lunch. We're back in the average daily temp around noon, because this is halfway, right? So this is at 12 hours later. So t equal 12. This is lunchtime. So that means at t equals 6, we find our minimum. So at 6 o'clock in the morning, we hit our minimum temperature. According to this model, I'm not saying this is exactly how life works, but this is what they're telling us. It's sinusoidal, so that means something. Sinusoidal functions are continuous, periodic functions. So it's going to hit that max, 89, at 6 o'clock in the afternoon, early evening, and then begin to cool off. And then at midnight, hit that average daily temp of 78 again along that midline. So that's our situation. And they're wanting to know, at what time do I hit 84 first? So I hit during a single day, I'm going to hit that average daily temp of 84 2 different times, here and here. They want this guy. They want to know, when do we hit 84 degrees first? What time of day does that happen? So we need to build us a model and then do us some thinking. Actually, do we even have to do a model? Let's see. We could probably brute force figure this out. I mean, there's symmetry here. So this is 5 units to the left. Oh no, that's 5 units down. I'm sorry. Yeah, that's probably wise just to go ahead and get the formula. All right, so y equals negative sine. We need to figure out the amplitude. The amplitude was 11 did that earlier. So negative 11 times the sine of, I need to figure out what b needs to be, what the coefficient in front of x needs to be. And then there is no shift left or right. And then there's a vertical shift to 78. The midline got moved from the x-axis all the way up to y equals 78. So the vertical shift is 78 units. So all we're lacking from having an equation is the coefficient in front of x. So just like last time, the observed period is equal to the normal standard period for the sinusoidal function, which is 2 pi, over b. But we're looking to know what b is. So I could go ahead and rearrange and solve for b before I plug in any numbers. That's how the physics folks do it. So that would be b is equal to 2 pi divided by observed period, OP. So b is equal to 2 pi divided by the observed period is 24 hours. Here's hour 0, midnight. Here's lunch, 12 hours later. Here we're back at midnight again. And we've completed our cycle. So it took 24 hours for that to happen. And then simplify that fraction. So b is pi twelfths. Okay. So that's our function. And basically what we want to know is, when does the graph of this function intersect this horizontal line, y equal 84? Because that's what I'm looking for, an output. Remember, in this problem, the output, the y values are degrees, the temperature, and the input is the number of hours that have passed since midnight. So what we're looking for, I'm kind of mixing this up. If I call it t one place, I need to call it t everywhere. So I'm looking for the time t. What time t do I hit 84 degrees first? And I know there's 2 places where I hit it in a single day, a single 24-hour period. So basically, I'm looking to solve that system of equations. So I could either literally let the output equal 84, put an 84 right here, and solve for t. That's one way to do it. But with Desmos at our fingertips, why would you? Why would you? So I'm gonna modify what we got here. And we don't need any of these points from the last problem. All them out. And let's adjust this. So that needs to be an 11. That needs to be, what did I say, pi eighths? Pi twelfths, what was it? Pi twelfths. And then plus 84. Plus 84. Not 84. Oh, what was the midline? Come on, guys. 78. 78. All right, so that's our function. And then I need to find out, when does this system of equations, what points do they share? So I need to know when the horizontal line y equal 84, which is 84 degree Fahrenheit temperature. And so I need to either scroll, or go in here and change. All right, so there's our period. So it starts there. It ends here. Here we are at 12 hours. We're at 78 degrees, just like we ought to be. Here we are at 24 hours. Again, it's 78 degrees. So that's our midline. We hit 84 degrees the first time at 14.204 hours. 14 hours and 204 thousandths of an hour of the next hour. In other words, about 20 minutes-ish. Basically, you're saying 20 hundredths is what part of 60 minutes. So you can actually figure out how many minutes. So 14 hours and some chunk of minutes. 14.204. That's our answer. So it took 14.24 hours to heat up to 84 degrees. There you go. Okay, a rabbit population oscillates 10 above and below average during the year, reaching the lowest value in January. The average population starts at 700 rabbits and increases by 110 each year. Find a function that models the population P in terms of months since January. All right, this is a doozy. Okay, so this was going to blow your mind. So I have P for population. All right, so it says its lowest value is in January, and we're starting in January. So that's time t equals 0 is January. The average population starts at 700 rabbits. So here we are, our population intercept, our p-intercept, is 700 rabbits. And then it increases. So it's at its lowest value in January. So then it increases by 110 each year. And it oscillates 10 above and below average during the year. All right, so let's first ignore this increasing by 110 because that's just a whole another level of complexity. So if that bit wasn't there, we ignored that little tidbit first. Let's just figure out what that would mean. So that means my minimum would be here at 700. And then I would hit, let's see, it oscillates 10 above and below average during the year. So this is, and it says this is a minimum. So then I'm going to hit a peak. I'm going to come back down, hit another minimum, hit a peak, then a minimum. All right, so my peak says I oscillate 10 above and below the average. So here's my average, it's the midline. So the average is 710. So P equals 710, Y equals 710. Then I max 10 above that because it says it oscillates. That means it bounces back and forth. 10 below, 10 above. So that means the maximum population occurs at 720 rabbits. All right. But now the problem is this 110 here. So this would be all fine and dandy. All right. So now how are we going to figure out what the period is though? We need to unpack this a little bit more. A rabbit population oscillates 10 above, and 10 below during the year, reaching the lowest value. All right, so we're going to assume they mean it just oscillates once. It peaks and then comes back down because of cold and starvation and predators or whatever. Maybe hunting season for rabbits is in, there's not such a thing, but in October, November. All right, so that means it would finish. So that means my period would be 12 months because our time units are months here. We're starting in January, we're ending again in January. So it completes one cycle in one calendar year. So Observed period equals your standard period for the sinusoidal function cosine. Oh, by the way, it would be cosine, right? Because remember, sine goes through the midline, and which is the origin if you haven't had a vertical shift. But cosine, unless it's been shifted enough left or right to force it to happen, your basic old cosine function doesn't go through the midline to begin with, at the vertical axis. So cosine is the one to use. And it's been reflected because usually cosine starts up high and then comes down, then does its thing, therefore, but back and forth, left and right all the way, forever. So we know it's got a negative in the front. We know its cosine makes the sense to use. The observed period is equal to 2 pi over b. We're solving for b. So b is equal to 2 pi over the observed period. So that's 2 pi divided by observed period is 12 months. So that simplifies to pi sixth. So our b, our coefficient in front of x, is going to be pi sixth. So this is what we have so far. Y equals negative, and then our amplitude is 10. That's what it oscillates above and below the midline. Down 10, up 10, down 10, up 10. So that's our amplitude. 10 cosine of pi sixth times t, where t is months, plus, now normally, see, I still haven't taken this into account because that sucker makes it harder. All right, so normally, if that wasn't there, then we would just say plus, and then this guy right here happens at 710. So it would be just 710. Like that, because that's how much it was shifted. That's how much the midline was shifted. All right, but this isn't the problem. So let's take into account and unpack this other twist they put in here. It says the average population starts at 700 rabbits and increases by 110 each year. So what's going to happen is my average of 710 oh wait. Oh no, I misinterpreted this. My bad. My B. Let me fix it. That was on Friday when you're listening to The Cure. Can't focus. All right, so it says that the average population starts at 700. So the average population starts at 700 in January. That's the average population in January. But in January, we're at our lowest value. I didn't take that into account. So that would be, and it oscillates by 10 above and below. So in January, on January 1, I'm at 690. That's what it's supposed to be. So that my peak, I'm at 710. And my average is 700. All right. So if this little increase by 110 each year thing wasn't there, then my equation would be that, because that's the y-intercept. That would be the y-intercept, and it would be the vertical shift, 700 units. But it says that it's going to increase by 110 people, 110 rabbits every year. So I'm not flat here. So by January of the second year, I'm not here. This thing has been steadily rising so that by the beginning of year 2, my average isn't here at 700. It's going to be here at 700 plus 110, 810. So this makes the graph look kind of funky. It's going to actually go like like this. My midline, in other words, my midline is not horizontal. My midline has a slant to it. And so see right here, instead of being here, it's going to be 10 above this midline. So your graph's going to look kind of funky. It's going to look something like this, like that. So how do I figure that out? I need to add to be able to account for this increasing population, increasing yearly population by 110 units. It's going to be 110 over 12 times t. It's the slope of the slant line. So in other words, this guy right here is basically a linear equation. So I'm melding together the sinusoidal function here and this equation of the slant line here. So I lost my music. I was enjoying it. That's probably why I wasn't able to concentrate. So then it'd be plus, and this will simplify. You can divide out 2, so you get 55/6 times t plus that initial y-intercept. So this is just a slope-intercept form of the line, but it's it's the equation of the midline. So let's graph him, see what he looks like. See if it makes sense. That's the important thing. Alright, so, excuse me, -10 times the cosine of pi 6 times t, let's use t, plus the sloping midline having slope 55/6 t plus 700. Let's do 2 things. Let's get us a scale on the y-axis that we can actually work with here. So, -2 to 2000. And let's get us to go very far to the left, and then we're going months. This is t is in terms of months. So let's go for about 3 years, 36 months. And then let's change the scale on the y-axis. Let's go by, I don't know, 50s. Hundreds. Ooh, Braille. How'd that happen? That's cool. All right, let's graph the midline in there so you can see that. We'll graph it dotted so you don't get confused. It's not really part of the graph. It's just a characteristic of the graph. Blah, blah, blah. Let's make him dotted, not so thick. Okay, then let's zoom in. All right, so here we are. So, all right, so the average rabbit population at the beginning of January was 700. But it said in the instructions that you hit your lowest value in January and that it oscillates 10 above and 10 below the midline. So this guy right here should be 690, and it is. And then here, 3 months later, you hit your average. It's kind of a rolling average. The average is always increasing. And then along about 6 months, you hit your peak, which is 10 above the midline. So if I looked at, so that's 755, and this is 765. So I'm 10 above the rolling average. This, all right, then at September 1, I'm back to the average, so they're the same. So the population is equal to the average population. Then I'm rolling in to a minimum at the end of the first year. But notice that this 800 value is 110 units larger. So this average of 800 in January of the second year is 110 higher than it was back here at 690. So 1 year passed and my average increased. My average population increased by 110 rabbits. I am at the minimum again, but it's a higher minimum because I'm forever increasing at a rate of 110, average of 110 rabbits per year. That's a doozy. That was a lot to unpack, a lot to interpret. So what's the question they asked? I answered the question. Find a function. Okay, so there's our function. And let's just make sure that I'm not making stuff up. And well, they wrote theirs. They ain't writing slope intercept form. We're same. Okay, number 5. A fish population oscillates 25 above and below average during the year, reaching the lowest value in January. Okay, so very similar to the last one. The average population starts at 850 fish and increases by 5%. Oh, so this is a constant increase in percentage. A constant percentage increase, that's an exponential function. Have we done exponential functions? We haven't even done those yet. So this is going to be tough for you guys. So let me help you out. So I've got T and P for fish population. So it says that we start at a low in January. So that means that we're going to use cosine again, what that really means for us. The average population is at 850. So my average is 850 up here. But I'm not at the average population in January. I'm below the average. I'm 25 below. So I'm at 825. So 825 is my first point. And then every month I'm increasing by 5% my population. So that's exponential growth. And the way you would model that, friends, is you need the basic exponential function growth model. So let's have a little look-see at that. So A sub t, and this would be our ending population for our exponential growth model. So I'm not even worried about the trig part right now. We're just looking at exponential functions. So a sub t equals the initial population, a sub 0, times b, the growth factor, how much you're growing by, the base, the thing being raised to a power, to the t power, where t is your time unit. Here it's months. So this is your basic, your generic exponential growth function. And so for us, in this problem, a sub t equals the initial population, a sub 0, your initial average population, because average is what's increasing by 5%. So the initial average population of 850 times 1 plus the growth, which is 5%. So 1 plus 0.05, we're going to use that as a decimal, not as a percent. So 1 plus 0.05, meaning the b value, the growth factor that we'll use in our formula, is 1.05 to the t power. So this basically is the equation of our midline, or mid-curve, I guess you call it. So it's not going to be like the last one where it was a constant, because it was a constant rate of change, so it's a linear. This is going to be exponential, so it's going to go up, look like this, zoop. And then you're going to have go above and below the line as it goes, like that. All right, now as far as what is the equation, it would be, let's see, let's build it. So it's going to be negative because it's below, it's been reflected. Cosine normally starts above the midline, not below it. So it's going to have a negative, and then the amplitude is it's oscillating above and below by 25 units. So that's my amplitude, 25. Cosine is what makes sense here because it starts below the midline, not on the midline when you're on the vertical axis. So negative 25 times the cosine of, again, it's going to be pi sixth because it's completing its cycle in 12 months. And so go back, look at the arithmetic for the last problem to see where we got that b value. It's going to be the same. So pi sixth t, there's been no shift left or right, so there's no phase shift. And then plus the vertical shift, which is basically the equation of our always changing midline. So it's this guy, 850 times 1.05 to the t power. So that's a doozy. That's cute. So let's graph him, see what it looks like. So y equals negative 25 cosine pi 6t plus 850 times 1.05 to the t power. It'll be hard to get a good look at this. All right, then let's do the midline same way. Let's have it kind of dotted so we can track it, kind of see it. 850 times 1.05 to the t. Other stuff out of there. All right, so that's our dotted midline. And we just need to figure out what in the world we need to do to be able to see it. All right, so let's go from November of the year before. Let's go 2 years ahead. Remember, this is t in terms of months, so 24 months out. And let's go, we don't need anything negative. I guess it's nice to see the x-axis. And then, I don't even know, 20,000? There we go, we're starting to see it. All right. All right, so there's 1 year. So here we go. So there we are at 825. We're 25 below the average 850. And then we hit the average in March, and then by the end of the second quarter, which is July, is we're at, I can't find it. Let me just do a vertical line. So we'll call that T equals 6. Didn't like that. So X equals 6. There we go. I wonder why that confused it. All right, so here we are. So the difference between this peak and this value at the midline should be, what, 25 units for back? So it should be 25 apart. So if you subtract 25 from this 25 from 1164, you get to 1139. So we're 25 above the average. Remember, the average is ever increasing. And then by September, we're back at the average again at that time. Then here we are at the end of the first year. And again, we are 25 below. Oh, it doesn't go. It's easier to get the points. All right, so at the end of the first year, our average is 1526. So 1501 is going to be 25 units below the average, because that's what it says. At the end of the year in January, we're always 25 fish below whatever the average is. But of course, it's a bigger average. By the end of the first year, the average has increased to 1526, all the way from an average the prior January of 850. And so it's experiencing exponential growth. That's an interesting problem. Non-trivial. All right, number 6. Last one, actually. A spring attached to the ceiling is pulled 9 centimeters down from equilibrium and released. The amplitude decreases by 14% each second. The spring oscillates 20 times each second. Find a function that models the distance d the end of the spring is from equilibrium in terms of seconds t since the spring was released. Okay, that's a whole lot to unpack. Assume that the spring is pulled from equilibrium in the positive direction. All right. So they're saying don't think literally, like here it is hanging from the ceiling, and so you're pulling it down or one in the negative direction. They're saying don't view it that way. That's all they're saying. So view it as if you're pulling it up. So for whatever reason. All right. A spring attached to the ceiling is pulled 9 centimeters down from equilibrium. All right, so we got this little weight, and it's just hanging there. It's just this calm. It's at this equilibrium. It's at a state of rest. And then it's pulled down 9 centimeters. And released. And it says the amplitude decreases by 14% each second. So it's going to come pull down and release. It's going to bounce around, right? That's what springs do. And when it comes back the next second, and the spring oscillates 20 times per second. So find a function that models the distance d the end of the spring is from equilibrium. Okay, so this is very similar to the last one. except instead of having an increasing situation where your midline is going to follow along an exponential growth model, this is an exponential decay model. Your amplitude is decreasing at a constant percentage. So we would model that with a midline that's going to look like this. Okay. So let's first handle that part. What's the equation of the midline? So it's going to be, well, let's look at the basic formula, standard form of a decay function. So that's going to be y equals the beginning state or beginning population when we're talking about growth. The beginning, the initial stretch, the initial amplitude, yeah, times the rate of decay, the decay factor. And so that's going to be, we're losing 14% from the 100% that we start with. So that's 86, but as a decimal. So our base for our exponential decay function is going to be 0.86 to the t power. So this is the equation of our midline. And that dictates our amplitude. This is a, so we normally have a constant as the amplitude, like 8. You know, I go up and I go above and below by 8 units, the midline. All right, but this is it's not a constant. It varies, and it varies at this constant decay rate of 14% per second. So, all right. So normally we'd have y equals. Let's see, we're starting extended, so we're not starting at rest. We're starting with it pulled down, so that's going to be cosine because we're not starting at the midline. So that's going to be just your general form for cosine. It's going to be amplitude times the cosine function times bx. We have no shift left and right, so we don't have to worry about a phase shift. And then that's it. Yeah. All right, so our height at any time t, that's supposed to be a t, not an x. It's going to be this not constant amplitude, but ever-changing amplitude. So it's going to be y equals 9 times 0.86 to the t power, that's my amplitude, times the cosine of bt. So what we don't know is the coefficient in front of x. All right, so observed period equals the standard period for the sinusoidal function cosine, which is 2 pi, divided by b. Dot, 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 solve for b. So b is equal to 2 pi divided by the observed period, which is 2 pi divided by, what is the observed period? 20 times a second. All right. Oh man, this is cruel. All right, we haven't even talked about this yet. So that's frequency. You know, number of times it oscillates per unit of time. That's frequency. So 20 times per second is equivalent to how do I want to say this? Let's think about how long does it take? What's the observed period? So it's in 1/20th of a second. So if it's oscillating 20 times per second, that means it completes its cycle, every cycle, in 1/20th of a second. That way it completes 20 cycles in 1 second. So it takes 1/20th of a second to do one cycle, in other words. So the observed period, or cycle, is a 20th of a second. So observed period is 1/20th. So therefore, 2 pi divided by 1/20, why did I write the same thing twice? 2 pi divided by 1/20th is the same as keep, change, flip. 2 pi times 20 over 1. So that's 40 pi. That's B. So that's the coefficient in front of our independent variable. So it's 40 pi. So that, believe it or not, is our function that models this situation. That's a doozy. And we accomplish what we need to accomplish. Find a function that models the distance d. Let's call it d. D for distance. Distance d, the end of the spring is from equilibrium in terms of seconds t, since the spring was released. Assume that the spring is pulled from equilibrium in the positive direction. The only difference that last statement makes is, if you didn't interpret it that way, then you'd have a negative in front of this thing. It doesn't really matter. So yeah, that's it. Let's make sure. Yeah, there he is. Ding, 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 ding. All right, so let's take a look at that for fun. So what did I say? That was a 9 times 0.86 to the t power. Take that guy out. Times cosine of 40 pi times t. So that guy needs to go away. That guy can go away. Oh, this is cool. I've got to get my y-axis under control. See, I don't need to go that small. All right. So this is it. So it starts here, extended by 9 centimeters, and then it's let go. And so by 1/20th of a second later, it's at its next peak. So it completes the cycle. But it's a dying cycle because it's losing energy. Gravity's impacting it. And so it doesn't make it, it never makes it back to 9 centimeters again. We know this in real life. This is how things work. It only made it to 8.932. And then here's the next 20th of a second. And so by the next 20th of a second, it only made it back to 8.865. And so forth and so on. That completes the next cycle. So we are 1/20th, 2/20ths, or 3/20ths of a second into this thing. We've completed 3 cycles. It only made it back to 8.799, so forth and so on. So it just keeps falling. So that by 1 second, it only reaches a max extended length of 7.74. So initially it was extended an extra 9 centimeters from its resting state. And by 1 second later, it only made it back to 7.74. And at 2 seconds, 6.656. All right, so how long does it take to get to its resting state? Here we are 8 seconds into it. It's already down to 2.693. So it keeps losing energy. So by 16 seconds, it's not even getting 1 centimeter. And it's getting close to being at rest. Anyway, that's our situation. All right, guys, have a great weekend. Hope you're not seeing this on Sunday night because you haven't done anything. You just sat around and looked at TikToks. Right, bye, guys. Happy Friday. Wrong place. There we go.